Okay. So we're going to cover the last chapter that we have to do before the exam, which is on Thursday. So we're going to go through chapter 13 on the outer planets. Okay. We didn't actually quite finish up on Saturn, so we're going to go through that. And then, actually, sorry, let me just go back for a second. As usual, the website has some review materials for the upcoming exam. So we click on lecture schedule, and then down on exam 3, there's a multiple choice practice test and also additional review materials from the book. I'll be going over the multiple choice test, practice test at the end of class today. Okay, so in the last lecture we got as far as talking about Saturn's atmosphere and the structure of the helium rain phenomenon that reduces the amount of helium that we see in Saturn's upper atmosphere. So now we're going to move on and start talking about the rings. So as we've seen already, there's a very large gap in the rings called the Cassini division, which is actually visible from Earth with a moderate-sized telescope. That's a dark line amongst the bright ring system. But when you get closer, you see all sorts of details that you can't see. Some of them you can't even see with the Hubble Space Telescope. You actually have to get closer with the space probe. And so we're going to talk a little bit about how all these little tiny gaps and things are related to the presence of the many moons that Saturn has. So the largest, the most significant example of that is the Cassini division itself, which was discovered by the astronomer Cassini. I kind of went through this very, very quickly at the end of the last lecture, but this is actually, this gap is actually due to a 2-to-1 orbital resonance that happens between particles which would orbit in that gap and one of the larger, one of the sort of significant moons of Saturn, which is Venus. So in a moment, we'll see another kind of diagram that shows us what the actual layout is of the orbits of the ring versus the distance to Venus. I'm not showing that right here because I want you to be able to see, what Venus actually looks like. Okay, so what we mean by this 2-to-1 resonance is that if we had a particle orbiting in this Cassini division, now Mimas is at a larger distance away from Saturn, so the period of Mimas's orbit is going to be longer than the period of the particles that orbit in this gap, because the particles that orbit in the gap are closer to Saturn, right? So Mimas is going to have a longer orbit. Now it turns out that at Mimas's distance, relative to this distance for the gap, for every 2 orbits of the ring particles, if there were any in that gap, there would be exactly 1 orbit of Mimas. So that means if you look at this configuration we're seeing right now, if there were particles in the gap over here, then 2 orbits later, they'd be there again, and Mimas would be here again in the same spot. And that periodic reoccurrence of this kind of alignment allows Mimas's own gravity to give a slight tug to particles which otherwise would be happily orbiting at that gap radius. Okay? So if it wasn't for Mimas, we wouldn't have this gap at all. It would just be full of particles which are happily orbiting around, not being perturbed by anything. But at that particular distance, what you have is an orbital period that's half of Mimas's orbital period around Saturn, and that's what creates the gap, because Mimas is able to periodically exert this little tug. Any particles in that gap will feel that tug every other orbit, and that tends to clear them out. So this is what we call a 2-to-1 resonance. Now you notice it's the largest gap that we see amongst the rings of Saturn, and that's because it's a force that's most frequently enforced. All right, so if you think about it, you can have all kinds of relationships between Mimas's period and orbital periods. It doesn't have to be 2-to-1. It could be any old ratio that you choose. It could be 3-to-2 or 4-to-5 or something like that. But those kind of oddball ratios are less frequently enforced than a 2-to-1 ratio like we're seeing here. Here, every other orbit, it feels a tug. So that's a very profound effect, and that's why we see such a large gap. Okay, so let's now look at an image that gives us a better idea of the spatial scale that we're actually talking about. There's the rings, there's the Cassini division, there's Mimas. So the significance of Mimas is that it's the closest large satellite of Jupiter. It's not the largest satellite. Actually, Titan is the largest satellite. It's not even on the scale. But it's a pretty significant satellite here, and you see it is farther out of the gap, so every 2 orbits of ring particles, you have 1 orbit of Mimas. That's the resonance I was talking about. Now, let's see. So we also have numerous other gaps and rings, so we'll talk about how those are related to some of the other orbits. A classic Voyager shot in the visual band, which again shows you this very detailed structure. We have Earth there as a scale. This is another Voyager shot that was taken when Voyager flew by, just showing amazing detail. You actually get the impression that the closer you zoom in on these rings, the more structure you're going to see. It doesn't, I mean, we actually really haven't run out of structure, if you will. Because even if you look at the smallest patch on this, you still see these little grooves, right? And that's because of the presence of all sorts of these resonant kinds of ratios, not only with Mimas, but with any other satellite that you want to choose, like Enceladus there, Tethys, Dione. They can all have these weird integer relationships with orbits in the ring system, and that's why you generate so much structure, because there's so many different ways that you can build that kind of an integer relationship. Okay, so the Encke gap, which is right there, the Encke division, or Encke gap right there. You don't see it real clearly, but there's a little bit of a dark groove right there. That's actually due to a 5-to-3 resonance with Mimas. You see? The Encke gap is a little farther out than the Cassini division. So what that means is that the Encke gap particles, if there were any particles in that gap, they would take a little longer to orbit around than the Cassini division gap particles would. And that's why you see that the resonance ratio is 5-to-3. So for every 5 orbits of particles that were in the Encke division, there would be 3 orbits of Mimas. So that's why the gap is so weak, because particles in the gap there, every 5 orbits, they line up with Mimas and they get that little touch. But that's only every 5 orbits, not every 2 orbits, like it was in the Cassini division, right? So the Encke division is weaker because it's less often enforced by the gravity of Mimas compared to the 2-to-1 ratio that we see with the Cassini division. So this is basically the kind of game that we play. You could actually put together any kind of ratio you want. Like here's a bizarre one. The outer edge of the A ring, which is over here, actually is due to a resonance with Janus, which is a little farther out. And Janus is a little farther in, sorry. Janus is right there, just outside the A ring. That's why the ratio of 7-to-6 is such a, 7-to-6 is pretty close to 1-to-1. It's not exactly the same because these particles at the edge of the A ring, for every 7 of their orbits, Janus will orbit 6 times. So it's, so every 7 orbits to get this effect. And also, by the way, notice that Janus is a pretty small moon there. But the reason it still has an effect is because it's pretty close to the A ring. So even though it's a small satellite, it still has an effect. So the bottom line is that there's, we think that because it turns out that there's many, many moons. We haven't really stated a figure yet, but it turns out to be over 50 moons orbiting around Saturn. And we think about all these weird ratios you could get. We think that explains all this very fine structure. They all represent gaps that, if a particle were in the gap, it would have some kind of integer relationship with an orbital period of a moon. But the main point of this particular slide is to show that Voyager actually saw these transient spokes. So these are features we don't really understand very well. We think they may represent the impact of a fairly large mass of some kind into the rings, which then got sort of obliterated and got its ventrals spread out in a very undignified manner, and created this transient spoke phenomenon, which was never seen again. It was just seen when Voyager flew by. Subsequent space probes like Cassini that's there now has not seen anything like this. So, all sorts of strange things can happen in a very complex system like that. All right, so I mentioned Saturn's moons. We'll talk about Saturn's moons. There's currently over 60 known natural satellites. The number actually fluctuates a little bit from year to year because space missions discover more moons around Saturn and around Jupiter, too, for that matter. We're in the outer solar system now, so the objects that we're seeing are completely unlike our moon. They're really almost more like cometary bodies with very low densities, down to around 1 gram per cubic centimeter, indicating a very icy composition. This is not surprising because, again, we're in the outer solar system. There's not going to be a lot of stony material, a lot of silicate material. Most of that stuff is concentrated near the sun due to this process of solar system-wide differentiation that I keep talking about, where the heavier material, like the uranium, the iron, are going to settle closer to the sun because that's the center of gravitational attraction in the solar system. So again, it's like a rock sinking to the bottom of a lake. You know, the reason a rock sinks to the bottom of the lake is because it's more dense than the water. The reason the iron is closer to the sun is because it's more dense than the lighter gases, so it tends to kind of, in almost like a buoyant way, move down toward the sun. So in the outer solar system, mostly icy and gaseous compositions. We'll see that 1 gram per cubic centimeter is actually pretty close to a cometary nucleus type of density. Okay, by the way, another point about this is, since these are icy bodies, we can presume that they're pretty much primordial. They were never melted, because when you melt things out there in the outer solar system, they turn to vapor and they kind of move away. They don't usually re-solidify. So these are probably primordial bodies which were never melted by the heat of formation of Saturn because they were far enough away. Just like the outer Galilean moons of Jupiter, like Callisto, the outermost of the Galilean moons, is a very icy object which is undifferentiated inside itself because it was shielded from the heat of formation of Jupiter by being at a large distance. Pretty much all of Saturn's moons are like that. Titan is the most exceptional moon around Saturn, and probably the most exceptional moon in the entire solar system because it's the only one that actually has an atmosphere. Still is quite icy in composition with a density of only 1.9 grams per cubic centimeter. Has this distinctly reddish composition because of a lot of methane. Okay, so here we see to the scale of the moon. It's a bit larger than our moon. It's actually about the size of Mercury, planet Mercury, or the Galilean moon Ganymede. Now, let me just flip to these websites real quick because Saturn and Jupiter, it turns out, have a long-running kind of friendly rivalry about who has the most moons. There's really not too much to brag about in the outer solar system, so it kind of comes down to the number of moons we got. And if we look at Saturn's moons here right now, as of right this second, there's 53 of them. But there's also 9 provisional moons. So remember those numbers, 53 and 9. So if we add in the provisional moons, it's 62, right? Okay, so let's see, this is Saturn, right? Yeah. So 53 and 9. So now let's look at the latest tally for Jupiter over here. What we see in the case of Jupiter is 50, but then there's more provisional moons. So there's a big controversy between Saturn and Jupiter about who's really the winner here, because technically with 53, Saturn has more moons. But if you throw in the provisionals, then Jupiter has 67 versus Saturn's 63, right? So there's a little thing going on there that you might see, occasionally they kind of Facebook harass each other a little bit about who has the most moons. It's not very common anymore. All right, so if you look at Saturn, we're seeing the moon system with the sizes of the moons to scale, not the distances, just the sizes here. And so obviously Titan is, clearly the dominant moon there. It's a gigantic body. It's larger than our moon. All of the other moons of Saturn are actually smaller than our moon. And again, most of the moons of Saturn are very icy in composition and without an atmosphere, but Titan does have this atmosphere. Now, if we look back at, this is an image similar to what we looked at before, we see again that the moons that cause the resonances are the relatively inner moons, right? We really don't see any resonances with the outer moons because, like, if you look at Rhea out here, there'd probably be 20 or 30 orbits of any ring particle, during the time of one orbit of Rhea, because it's so far out. So that means that there's really not much of an effect. So if you got to orbit 30 times in order to regain this alignment, you're not getting that kick very often, so you're really not going to get the gaps. The gaps are mostly due to the inner moons. Now, you notice we don't see Titan here anywhere. Well, actually a couple things. First of all, the major moons here are in the same plane. They're almost like a mini solar system in the same plane. But we don't see Titan. If you look at all these names, you do not see Titan anywhere. Titan and a few of the other moons are way out, farther out. So Titan is at a much larger distance.